And thank you all for attending this keynote. I think Mark laid out a broad contours of what 5G broadcast is. I'll get into the mechanics of 5G broadcast or 5G offload, and also tell you it's not just a marketing spin, just to jump on the on the 5G bandwagon, but it is genuinely an important concept. So if you look at the demand side problem, I think Mark mentioned that as well. You'll see that video consumption on smartphones is exponentially increasing. In fact, where I come from in India, the last couple of years we've actually had I wouldn't say even higher than exponential growth in the consumption of video on phones. It's largely due to an operator called Reliance Jio, and most people in India, mostly in rural India, are actually watching more video on their phones than on TVs. And there's a whole lot of other factors, and I believe that happened largely because of the price wars and the price points that Jio offered for data plans. And I believe in developing countries and world over, you would start to get this phenomenon replicated everywhere else. And also, apart from the phones, you also have a new phenomena here of the cars, right? And cars like Tesla, while they're not full, well, there is a drive to go to autonomous. Even today, I mean, imagine downloading from. I believe Tesla does a download firmware update probably every other day. So if you have 6 million cars, and then if the other big car OEMs join in, you have about, just in the US, about 50 million, 60 million cars getting downloaded with new software, new updates, and so on. And no amount of 5G throwing spectrum at it is going to work. I call this the fat pipe syndrome. So we have to go from a fat pipe to a smarter pipe. So given the infinite elasticity of the broadcasting pipe, the one-to-many, this application is very well suited for the broadcast pipe. Also, the supply side issue, where I come from in India, I think the ARPUs are the lowest for telecom operators, but the spectrum prices are probably the highest in the world. So you have what I call the natural, supply side issues, natural crunch of spectrum, especially in the sub-gigahertz band. But there's also artificial barriers that I believe that's been created. It's largely because of regulatory and technology policies. If you look at the way we design and deploy networks, generally, so far we have always had static provisioning of networks, which means we always design for the cell edge and the worst case performance. And we've always designed for the worst case, and rightly so, because you want to keep the cell edge or the, I mean, in a telecom network, the cell edge or the broadcast edge in the case of broadcasting networks, and give a quality of service there. But if you look at real world users, especially for mobile users, right? Most users would be around the center of the network. Now you're penalizing the average case for the worst case scenario. And also, David's question rightly was, why is there not a single standard? I would argue the other way. In fact, we should go to a point where we should have infinite number of standards. So you have to respond to it with an architecture where the radio environment itself is a very dynamic environment. So it changes every minute based on traffic conditions, based on interference profiles, and a whole bunch of other things. So therefore, you should, given the kind of semiconductor complexities that are available today and the compute power available today, we should be looking at hyper localization of standards in some sense, and not necessarily worry about of unification of these standards, and that we believe is the future. So then, what is 5G broadcast? It's as Mark pointed out, and a very important aspect of this is a non-3GPP access. And ATSC provides a good, ATSC 3.0 provides a good candidate, but it's more than that, right? It's like I said, 5G is about three major points. For me, it's virtualization, disaggregation, and densification, right? So you have a virtual core. The biggest the biggest point that 5G puts forth is actually the virtualization of the core. And then you have disaggregation, which means you want to run more and more software and potentially modems on the infrastructure side on commercial off-the-shelf platforms. So eventually you would also get to a device which actually also can be run on a COTS device, on a COTS platform. And that's where we need to get to. Densification is, like Mark pointed out, you localize the network to increase the capacity. If you look at today, if you also look at the way CDNs have developed, content deployment networks, they actually are in response to the nonlinear OTT video consumption. So depending on the spike in the user, there is a term called elasticity in CDN networks, that they have to be elastic. So they have to respond to by spawning of new servers or kicking off new threads in certain servers. So contrast that with a broadcasting pipe, which has actually got infinite elasticity, the one-to-many thing that Mark spoke about. And there's a need to also innovate on that aspect, to have an end-to-end service that actually gives you a core analytics engine that decides whether the video is going viral, whether the videos can be offloaded to a broadcast pipe from the nonlinear perspective, and also a CDN that actually a new CDN architecture that not only responds to this elasticity but also comes close to the edge. So all this thing about MECs and the edge computing is in line with it. So if you look at it in the future, given the fact that storage on mobile phones is so cheap, you would also have a CDN on the device itself, right? And then you could actually go to a push architecture where you would actually start pushing content into the device based on the analytics engine. And finally, a new paradigm in broadcasting in terms of the cellular architecture, a cellularization architecture. Those of you familiar with 5G can relate to this slide. So this is one of the reasons why we call this as 5G broadcast. So the last part, the bottom part is what we have added to this stock slide that actually is presented in most books and papers. The broadcast slides is actually an end-to-end service, end-to-end 5G service that has its own overlay, it has its own virtual components on the network, and its own service side on the user consumption patterns. Not only are we just talking about cellularized architecture that Mark spoke about, the new transmit architecture also has to be dynamic. So think of it. I mean, if you're rolling out a network and you want the broadcast pipe to not just carry video but potentially unicast traffic. In some scenarios, you would want an MFN network, and in some other scenarios, you want a SFN network when there's a whole lot of similar content being watched in a particular cell. So you should have a transmit architecture now, which is also changing its color. So it's also software defined. That's the reason we need a dynamic transmit architecture. Typically in the broadcasting arena, we have, depending on the country, regulations, and a whole bunch of other things, you have a reuse factor of 1 to 7. So which means your spectral efficiency is actually 1/7 of what is claimed by all this all of DVB or ATSC or any other standards. In the cellular world, while they talk about reuse 1, it's not really reuse 1 in the sense there's no interference cancellation. You still have physical layers which are from a decade old, where you operate in the interference-free regimes, whereas new physical layers should actually start to operate, have signal designs for interference-dominated regimes. So in cellular networks, typically the reuse one is implemented as joint scheduling in the layer 2, and it's really not that efficient. So the cell edge performance actually drops. So a lot of networks today, SINR is more dominant than SNR, and that results in a quasi reuse one architecture. In our scheme, we want to go to full-fledged reuse one scheme where the cell edge, you actually can remove interferers and actually build a new PHY for that. A quick taxonomy on the 5G broadcast. There's the device side versus the network side convergence. Device side is pretty easy to implement. The device, you got the broadcast content coming in on the broadcast network as well as on the mobile network, and then based on thresholding, the device changes the switches between the two. It's easy to implement, fewer touch points in the network. It benefits the users, but not the operators. You increase the bandwidth consumed because you're using both the pipes. Then there's the layer 1 versus the layer 3 convergence. Layer 3 is a non-3GPP access PHY, whereas the layer 1 is layer 1 is based on 3GPP. So the question is whether you do it at the PHY or the IP layer. Like I discussed, you need more payload optimized physical layers. So unicast networks are typically have low latency as one of their important parameters. But when you're carrying video, and therefore you can't use time diversity. Whereas when you're carrying video, you technically are not so worried about latency, but you want to use time diversity that's there in most video broadcast PHY standards. There are advantages of both the schemes. The obvious advantage has been stated that you've got a ready-made device ecosystem, but it's not really the optimal solution from a deployment perspective. They're not spectrally efficient as well. Also, I think there's a lot of data on this. We have done a reasonable comparison of the 3.0 variants and FEM BMS. We believe that you get a spectral efficiency of at least 2 bits, 2 to 2.5 bits more if you implement the 3.0 variants in a converged environment. What are the different implementation options, right? You could technically, as a broadcaster, you could just implement a standalone cellularized architecture where you have the advantages for a broadcaster are reduced capex and opex. You have more densification, better monetization because you've got a fatter pipe. So if you densify the pipe, and if you look at regulatory notwithstanding, you could technically have a 1 gigabit pipe on in a kilometer or a 2 square kilometer area, depending on how you densify for the UHF network, and that's very powerful. So you don't have to pay. You don't have to roll out $1 trillion of infrastructure as is required in the millimeter wave region. So you get hyperlocal LADs, and more capacity. And finally, the key piece, this is the ideal situation where you have a converged 5G broadcast, where you have an overlay. A broadcast overlay with a cellular network. So we have done some studies where typically every third or the fourth, depending on what frequency is being used, every fourth base station or eNode B actually would need a broadcast radio head or the cellularized small cell broadcast radio head. Coupled that with a analytics engine and a CDN, you could actually deliver content seamlessly to phones, to all kinds of devices, right? In a device agnostic manner. You also, the user wouldn't know where his content is coming from. So you wouldn't even know, and it doesn't even care whether the content is live, linear, non-linear, OTT, whatnot. He just has an application on his phone, and then he requests for video. Then the network intelligently decides what's the best scheme of delivery, given a bunch of cost functions. In fact, there needs to be a lot of more research on what those cost functions are and on how the scheduling has to happen. And a core piece of all of that is also the software-defined radio. And as you start to get to 22 nanometers, 14, and even 10. In fact, Samsung's latest 5G modem is on the 10 nanometer that packs in I don't know, a few billions of transistors. So as you get so much compute power, the obvious answer is to have more flexible architectures. I mean, that's the goal of computer science anyways, to keep raising the levels of abstraction. So once you do that, then this whole debate of whether my phi is better than your phi is irrelevant. It all then is decided by the network on what's the best physical layer or what's the best bearer channel that needs to be implemented. But what we need to still agree on is an IP pipe, is an IP layer convergence. So this architecture is actually a video optimized network. It is in some sense reimagining the video wireless internet, and as a very quick example, I'll show you how a use case OTT services can be deployed on this. So today OTT is pull, which means you start an application and you request for video. But here in the new CDN architecture and the new in the new transmit architecture, we could actually have a push OTT and a timed OTT, and you can have an out of order OTT delivered between the broadcast and the unicast pipes as well. And then that becomes a simple scheduling problem. These slides are available later, so I could take questions on this given the shortage of time. What are the use cases? Obviously, OTT and high viewership live events in stadiums where people are hundred thousands of people are watching the same content, and interestingly, even location services, right? So because you have so many of these BRHs around, you could actually deliver a terrestrial GPS. It's a very interesting application. You think about it. At the end of the day, all the stakeholders within the ecosystem benefit. The end user has a superior experience. The MNOs and the broadcasters monetize the spectrum and use the spectrum more efficiently. Thank you.